phase 4 is listed as worth 0 points. Technically, it's kind of just included in phase 3, because if you don't do phase 4, then we can't grade phase 3. So don't let that make you think that you don't have to do phase 4. Okay? Any questions about that? Okay. Yes.
I have a question about if you just create a version
So Mark Ogden, the main KDOPER guy, was kind enough to give us 85 VMs, which is actually harder than it sounds. There's a lot of resources involved there. If you know Mark Ogden, you happen to run into him, tell him thanks. It's like really awesome that he did this for us. But yeah. Okay. So everything we've been talking about so far is in the context of relational databases and structured data. So structured query language is the language for querying a relational database, at least the popular one. So just to kind of recap what that means, because there are non-relational databases. It just means the data is defined in terms of the relational model and relations, and queries are defined in terms of relational algebra. So that defines certain things, like a relation is a set of tuples, set meaning unique, which implies that every tuple has a key, every relation has a key or more than one key. But basically, the data is rigid. There's a very rigid model for what is valid data. Every student has exactly a UID, a name, and a date of birth. I cannot have one special student that also has a favorite sport or something like that. If I wanted a favorite sport, every student would have to have a favorite sport. You could maybe allow for it to be null, but every one of them would have to at least have that field. And that's the most kind of fundamental idea, but it allows us to add kind of additional rigidity and that's a good thing. So we get integrity constraints out of a relational database, meaning that we can prove certain things about the data. So domain constraints, like fields can't be greater than or less than some value, or can't be null or can be null. Key constraints, like uniqueness. Referential integrity, so foreign keys. If we have proper foreign keys, then it won't let us make an invalid pointer, or it won't let us delete the thing on the other end of a pointer. Things like that. And that's great. That means the database system is doing like all of the error checking for us, and proving that our data is properly formed. So let's think about let's say you're Facebook, and this is back in, 2004 or whatever, and SQL and relational databases are all the rage. And Facebook has gone through many, many versions. They add features all the time. So let's say version 1 is just storing people, like pictures of people and your friends. And then they add that wall thing, which I don't even know if they have anymore, but they had for a while. Kind of just like your personal page. You could draw things on it or whatever. And then they added this poke feature. I don't know if this is in the right order, and then they add that timeline thing that I don't really know how it works or what it does, but I know about it. And all throughout this, they are aware that their value, their commodity, is your data. So version 5, this tracking all manner of useful information, this is actually spanning all of this, but they're deciding what information they want to track. Probably the answer is just everything, but the more features and the more information they add, the more information they have to track. And then maybe version 6 is like suggest friends. That actually probably came way earlier, but pretend it came later. Let's think about this one actually. How would you, so let's try to imagine the tables in an SQL database that Facebook might have. You have your user, you have probably some table that says friends or whatever. So you have a user ID and another user ID saying those two people are friends. And the basic algorithm is go find all of your direct friends, and then go find all of their direct friends, and maybe even one level further. Find someone who happens to know a lot of the same people you know. How would you do that in like an SQL query if all you had was this one column saying person A is friends with person B? You'd basically have to do multiple queries, one for each level you want to expand in that graph. So the friends network, think of that as a graph. It is a graph. And then version X, whatever, they bought Instagram at some point. They were their own company. They had their own database. How did they suddenly take all that data and fit it into Facebook? Maybe they don't. Maybe they just leave it where it is and augment Facebook to have like pointers into the Instagram API or whatever. But the point is, social media stuff and modern web stuff tends to change rapidly. And you don't really know at design time, you don't really know what information you need to hold and what the relationships are in that information. So kind of vaguely, broadly describing this problem is the legacy database problem, meaning if you started with some database, a relational database in particular, and it's been in use for a very long time, that means the relational model used in that database is integrated with every single part of the software. So the JavaScript, the C#, the link queries, whatever you're doing, like all of that is pretty heavily tied to the legacy database. And modifying that, especially as it gets bigger and more complex, becomes a more and more challenging problem. We've had people ask, like, say you have this old database with tons of tables, how do you actually go and like add a new column to some table when there are all these foreign key constraints to keep in mind, normal key constraints, just all kinds of issues. So basically the problem is the relational model is not very agile compared to like object-oriented programming anyway. And then this gets even worse in the modern era when the data that big companies are using, like Google, Facebook, and so on, it's changing so rapidly and unpredictably. A relational database may not really solve the problem. It will, but it'll be hard to do. And then imagine like what happens when companies merge or split. You have suddenly two databases you have to integrate together with different relational models, or you buy a bunch of data from some other company. It's a challenging problem. And what I'm leading to is there are other kinds of databases that help with this problem. One of the biggest problems with all this new data we're getting is that it's largely unstructured, meaning it's not going to come in these nice little packaged tuples saying like there is an X, there is a Y, there is a Z, and they are int, float, and bool or whatever with a rigid, well-defined type. So Merrill Lynch estimated, I don't know how they estimated this, but they estimate that like 80 to 90% of all usable business information is unstructured, meaning it's like a paragraph out of an email or something like that, or a memo that the CEO wrote to some company or something like that, just some kind of data. And obviously in order for a computer to be able to use data, it has to have some kind of known structure, unless you're getting into AI, like natural language processing. Okay. doing is database first design. And this works very well for relational databases. And the reason we did that is because the relational model is kind of a stronger definition than like the object-oriented model. So we design the database first rather than design the code first. And it works great for us because we know exactly what data we want to hold, and we're not Facebook, we're not going to add a bunch of new features to our LMS. But what this comes down to, like relational model versus object model. And when I say object, I mean like an object in a programming language. There's this long-winded term, object relational model impedance mismatch. So object-relational, meaning you have the object model and you have the relational model, and there's a kind of a mismatch. Impedance mismatch comes from like electrical engineering. So basically this means is the relational model does not fit the OOP model. As an example, let's look at like the OOP model has this notion of public versus private, or protection levels. The relational model has no such thing. It doesn't even have an idea of that. OOP model has methods. So a function or procedure can be associated to an object. Not really anything like that in the relational model. The relational model is defined in terms of relational algebra, which are kind of these like global static functions, if you will. They're not objects. Relational model has no such thing as inheritance. I mean, not really anyway. So there's no is-a. There's also not really has-a, so composition. There kind of is. You could say that a student has an enrollment record because there's a foreign key pointing to some other table. But it's not really the same thing as saying that some object lives inside of another object. And that is like fundamentally a part of the other object. On the other side, OOP has no transactions unless you have some fancy system library that implements them. But you don't write object-oriented programs with transactions in mind. If you have concurrency issues, then you're probably thinking more along the lines of mutexes. There are no isolation levels like in the relational model, or in SQL databases anyway. So just all these little things like fundamental design differences that mean it's not always going to be easy to match the relational model to your software model. For us, it was super easy because we started with the relational model and there's an automatic scaffolder that generates all of the code we need. Okay, but so getting around this object relational model impedance mismatch problem and other problems is this idea called NoSQL. And this started becoming popular, maybe like mid-2000s, late 2000s, and gaining more traction then, and is quite a bit more popular today. NoSQL is not a database or a language. It's a vague term meaning non-relational database. So the basic idea is you're not like tied down to the relational model. You don't have to define schemas and follow these like set and key rules and things like that. So it's more open-ended, basically. The relational model, the point of the relational model is that it's rigid and restrictive. It prevents you from harming yourself. Non-relational databases are intentionally more open-ended. You can kind of do more like whatever you want, which is both a good thing and a bad thing. But so how they work, I'm not saying that they don't use some kind of structured tuple. So a student has a UID plus a name plus a whatever. That is structured data, but what we're going to look at is semi-structured data. Meaning, it has some kind of form where you know what things are in it, but each individual thing within some collection of things doesn't necessarily have the same structure. The important thing is that it's self-describing, so it's tagged information. You know that there is a thing called X, a thing called Y, and then maybe some of them also have a thing called Q, and some of them don't. But you know what it's called, and you know kind of what values you might be able to look for in any given tuple.
So would JSON notation be an example?
Yeah, exactly. So JSON is the perfect example of self-describing data. Semi-structured data. If you had JSON where there was an additional rule that every JSON object had to have fields X, Y, and Z, then it would just be structured data. So let's go back to like the Facebook example. Even without rapidly changing features, even with like a fixed version of Facebook or some social media thing, a post may or may not have text. It might have pictures. It might have text and pictures. It might have a posting time stamp. It might have geodata, location, comments on it. Lots of different things that some of them might have, some of them might not have. And more importantly, this might suddenly change in the next version. So we're going to use self-describing data. We can just say, well, this post has something called text, something called location, and something called date. Some other post has something called text and something called comments, and none of the other things. But we need to know, we need to at least have a name for each of the things that they have. So JSON is the basic and most straightforward notation for self-describing data. You have basically key value pairs or field name value pairs separated by a colon. And the important difference here is that the data is described by itself instead of by a schema. So in a relational table, the data does not have to say, I am the name. Like being in the name column is what makes it the name. Okay, so let's say you need to add an address field to one record, but not all of them. So, okay, you just go find that record and add a new JSON field, put it back into some file or some storage somewhere. And the thing is, there's no schema to violate. So adding an extra field, or call it a column if you want, to one of them but not all of them is fine. Say you want to relate a customer to a new order. In a relational database, you would have a customers table, an orders table, and a some kind of key in between them, foreign key in between them. In this, if you have a customer with no orders, fine. If you have a customer that just made a new order, just put a new object inside of that customer, an order object. Or you could do it the pointer way, like the relational model would. Say someone declined to provide a phone number when creating their account. Okay, just don't add that field to the JSON object representing that customer. So semi-structured versus strongly structured, pros and cons. The good is it's adaptable. You can change it in any way you want without violating a schema. And it's easy to just integrate with another semi-structured database. Just add objects, point objects to other objects, or whatever. The strongest negative consequence of this is it's impossible to reason about the kinds of queries you can do. So with a relational model with structured tables, if I just gave you there are X students and Y classes, and I gave you some join command, you could tell me how many rows are in the result. Like if it was a natural join or something. You can easily reason about because you know things about uniqueness, you know things about foreign keys, how you know everything has a certain column. So not only can you reason about the data in the queries, but the DBMS can reason about the data in the queries. And that's how the plan generator is able to make optimal plans for most queries. Okay. So NoSQL and non-relational databases does not necessarily mean unstructured, but it's usually what it means is semi-structured, something like JSON. And there are lots of kinds of quote NoSQL databases. There's a question back there.
Yeah, there's NoSQL databases that optionally support things like indexes.
Yeah, NoSQL databases can definitely support indexes. Yep. But what they probably usually don't support is something like a join. So, that's kind of like one of the main operations of a relational database is a join. That's how you find and relate information together. Doing that in a non-relational database is kind of just like up to you, or up to however the system wants to implement it.
Is there a way to prevent anomalies, like create, insert, update?
So is there a way to prevent anomalies, like insert anomalies, update anomalies? Yes and no. Depends on the database, depends on the structure of your JSON things. So we're going to be talking about one called MongoDB that can do things like prevent duplicate inserts optionally, but has a harder time doing things like foreign key constraints. Okay, so lots of different types of non-relational databases. Columnar stores, graph databases, where like the fundamental operations that it supports are like graph traversal algorithms. So, find me a path from here to here, or find me all neighbors that are one edge away or two edges away, or something like that. The ones we're going to be talking about today are key value stores and document databases. So you may have heard of Redis or Oracle NoSQL. You've probably heard of Firebase, right? Some of you anyway. We're going to be talking mostly about MongoDB. So those Firebase and Mongo are document databases. So let's talk about key value, kind of what's the difference between these. Key value store is basically a hash map. It's like you set up certain collections or whatever, sets, and you can specify like what is the type of the key and what is the type of the value, and that's kind of, it's the most basic idea. And then a document database is a subclass of key value store where the value is what they call a document. That doesn't mean it's a file. Document usually refers to just like a JSON object, or some XML. Some snippet of XML would be a document. Okay. So Redis is one of, if not the most popular key value store database. It also supports other things. It's not just a hash map. It supports things like spatial queries. In some super fancy ways, it also supports range queries. So normally a hash map does not support range queries. It's fast, partly because one of its main things is that it's designed to operate on smaller data that can fit in memory. So you have some Redis server running somewhere. It's not going to have the problem of optimizing for page access. It's going to like disk painting. It can do things like assume that it's operating within memory, and it's written in C. SQL, MySQL is probably written in C too. Anything that you really need to be fast, you're probably going to write in C or C++. So this key value store thing, like, okay, so you have a hash map on a server somewhere. Great. It can actually do more than just lookups and inserts. It can actually order things. So here is the notion of an ordered set, where set means it holds unique things. The most basic and an optimal way to implement a set is a hash table, but an ordered set, you need to impose some kind of ordering. So what you do is you basically have a hash table plus something like a BST or a linked list, where the nodes in the hash table have a pointer to the nodes in the list, and the nodes in the list have a pointer to the nodes in the hash table. So you can quickly do most operations. Insertions do necessarily get slower because you have to find the right spot to put it in the list. But then deletions, you don't have to go find it in the list. You use the hash table to look it up, instantly find it, and then instantly delete it from the list using that pointer into the list. Or it could be a tree, something like that. Turns out C#'s dictionary data structure is an ordered set, but they don't tell you it's an ordered set. If you insert things in the order, 1, 2, 3, and then you iterate over the values, you're going to get them in the order 1, 2, 3. It really annoys me that they don't tell you about this, and students fresh out of 2420 think that a hash map is ordered. They are definitely not, unless it's something else. Okay, and then, so that's it. We're not really going to go into using Redis or anything like that. But we'll look more at this thing called MongoDB. It's probably the most popular, among the most popular document databases. So its documents, what it calls documents, are just JSON objects. So it's grouped kind of similarly to an SQL database, where you have a database. Within the database, you have collections. That would be analogous to a table. So you'd have like a users collection, a books collection, something like that. And anything within any of those documents can have any structure it wants. The only really structure you're giving it is by putting it into a collection with a certain name. But that doesn't mean that it has to have any particular structure. So the hierarchy here, kind of what it looks like, is you have databases, just like in SQL. You have collections, similar to tables. And then documents, analogous to rows. But try not to think of, from this point forward, try not to think of rows or columns. It's a key value store of some key pointing to some JSON object. Okay, so let's look at how, kind of compare this to a relational database. So here is the relational model library. And I've actually optimized this a little bit by taking the checked out table and combining it into the inventory table. So I just have that holder column in the inventory table. So I've made it a little better, but even still I have 4 tables. And the reason I have so many tables is because I did decomposition to arrive at a normal form. Right? We talked about normal forms last week, and this is just following good, proper relational model in a normalized form. Here's the document version of a library database. So the whole blue thing is the database. The orange things are collections, so kind of like tables. And then within each collection are these little JSON things. Each one of those is a document. So a few interesting things to look at here. Joe is the only one that has an age. Anne is the only one that has an email address. Dan is the only one that has any books checked out. And the way that we say that Joe has no books checked out is by just not having anything called books in his document. Dune, for some reason, doesn't have an author. I don't know, maybe we don't know the author of some book. So there's no structure here. There's no schema, just JSON objects. The only thing relating people is that they are in a collection called people. Now, in reality, you would not just make it like totally arbitrary and random. You would have, probably every document would have at least some common field, or a couple of common fields. Like, in this case, you do actually need a key for these documents. In this case, name would be the key for people, and ISBN would be the key for items. Okay? But we only need 2 collections now, because the way that I say someone's checked out a book is I just add something to that person's document. Question over there?
Yeah, when you say key, like people have name as the key and adding a title, those have to be unique. So if
Yeah.
you search in name.
Yeah, key has kind of the same meaning where it means unique.
Okay.
So name is not actually a very good key here, meaning you couldn't have two people with the same name. Yep.
So if it has a key, does it have something similar to the index where we want to query it?
If it has a key, does that mean it has an index? Yes. So in MongoDB, you do automatically get something like the primary index. I don't know if they call it the primary index, but yes, you get an index built over the keys for every collection. You can also add an index on a certain field of your choosing. So I could add an index on email, even though there's only one person in there with an email address.
Can you add additional keys?
Can you add additional keys? Kind of. When you're creating an index, you can make it a unique index. So it'll prevent adding duplicates, and that's kind of the same idea as making a key. But what these keys do not mean is they are not the endpoint of a foreign key. So there's like no pointers here between these two documents, or these two collections. Okay, so MongoDB, much like MySQL, has a command line interface and other interfaces, and it has its own language. So MongoDB is not some standardized thing like SQL is. It's like a private company. It is free. I don't know, they sell some kind of business class support or something like that, but it's got its own language that's similar to JavaScript. So you're not doing things like select, where, join, things like that. It's more like you're writing code that's accessing a data structure. You can search for documents with a certain field. So there's no analogy to that in a relational database. Every row in a certain table has a field. It doesn't make sense to search for only things with a certain field. You can search for field value pairs, range queries, things like that.
So that'd be more like searching the thing for anything that doesn't have a null value. Like
Kind of, yeah. You could make an analogy that you could search for things that don't have a null value, but in a document database, you might have 1 million records and only like 2 of them have a certain value. It'd be really bad to store almost 1 million nulls just for those 2 non-null values.
I'm just saying on the relational database side, it'd be like having columns that have null, you're just searching for anything that has null.
Yes, essentially, yep. Okay, so we will play around with MongoDB a little bit, but let's take our break now. Okay, so it's running on this local machine, so I didn't say, go connect to this server or whatever. But that would be similar to MySQL. Okay, so I have my terminal here. I can do show databases, just like in SQL. And just out of habit, I'm usually going to put a semicolon on the end. Turns out in Mongo you don't need to. But so just as in MySQL, you have these like system tables, like the config table, admin table. I also have, or not table, database. These are databases. I also have my library database, and you can use library. So identical to SQL pretty much so far. Now you can do show collections, so not show tables, show collections. And I just have those 2 that I had on the slide. I don't need phones, I don't need inventory versus titles and checked out and stuff like that. So normally at this point I would do something like describe items or something like that. But there is no describe, because what describe does is it tells you the schema. There is no schema. There's basically no more information about items other than there is a collection called items. So we don't really know what's in it, but we can start doing queries on it. We can start pulling stuff out of it. So you can do, and this is where the syntax starts to look very different, kind of like JavaScript.
The collection
collections is analogous to tables, not columns. Yeah. So I can do database dot items. So that's one of the collections. And then I can just do dot find. And if I don't specify any other parameters, it's going to find everything in the items collection. And I call it items instead of books because maybe the library also has like iPads you could check out or something like that. And you just put them in the same collection.
Just curious, do you have to do db.items, or can you just do items.find and it will find?
Can you just do items.find? No. I actually did have to run that in order to answer that. I don't use Mongo too much, but so what we have here is, okay, so there's Dune. This is just JSON. Title, colon, Dune, comma, author, colon, Herbert, comma. What we also have in here, though, is every item has this object ID. That is the key in the key value store. So I didn't actually specify that ISBN should be the key. You normally would probably want to do that. Since I didn't, it has to make one up, just as SQL will make up a primary key if you don't specify one. Okay, so I don't really actually want to see that key. So this is kind of like, let's do a select where we get everything except for that key. And syntax, again, is going to be quite weird. But so what we do is we start out with putting a filter on the find. We have two sets of curly braces. The first one is kind of custom filters where we could do something like where the title equals Dune. The second one is kind of like the projection where you're saying give me only certain fields. So I can do underscore ID colon false. And that just means do not display the ID. Find everything, but do not display the ID. Okay, so there's my two books. Now in this other set of curly braces is where I can start doing things like title colon Dune. Okay, so kind of just like putting JSON into this weird like JavaScript-like function in order to filter things down. Let's see. So we can also do, so let's look at, db.patrons.find. And again, I want to ignore the ID. So we have Joe and Ben. Anne doesn't have an ID, doesn't have a phone number. Just to illustrate the fact that there is no structure here, it's semi-structured, there's no schema here. I have a patron called foo, I have an entry in here with a foo with a value of 50. So, you know, that is not a patron by any meaning of the term, but I can add anything I want. So I just added this JSON object foo colon 50. Okay. So let's say we want to find only the people that do have a phone number. So the syntax is, it's not, you wouldn't do something like phone colon whatever. You put that over here into the like field selection part of the query. And so what you would do is something like, there's this special function, $exists, and then with a value of true. So I'm saying phone where it exists, basically. And then let's see, I think I need one more curly brace. What did I misspell? Turd. Let's see. Oh, I need clear that I don't use Mongo a lot. Well, anyway, something like this would give you only the ones that have a phone. It does work. I have tried this. For some reason, the command I wrote here is not the right syntax, but points I want to make are, let me do just this complete find again. Different structure for it, potentially different structure for every item. Totally unrelated item. It's not that you would do this. This is just making the point that you can. You would definitely have some kind of common fields that everything in here has. Otherwise, your design would be just totally weird and a bad design.
So, can it do things like find how many collections have certain?
Yeah, so you can do like how many of them have a certain value for this field. It's very open-ended. You can basically write your own custom functions. I think I actually just realized what is wrong with my, I think that does go in here. So you would do phone colon $exists true. Yes. Okay. I had it in the wrong set of curly braces. I'm going to put false in. Okay. So let's start doing something that we might want to do like with the library. So let me go back to finding everything from titles. So the only one that I have a serial for is Hyperion. That's kind of indicating that I have a copy of that book, and I don't have a copy of Dune, but I know that it exists. So let's say we want someone to check out that book. There's our books. There's our patrons. How do I say that a patron has checked out a book? There's no column in here for saying which books have been checked out.
Just add a checked out.
Exactly, yeah. We'll add, maybe we'll call it checked out and have it point to the serial number. So db.patrons.update, meaning there's an existing thing in there that I want to change. And the syntax is kind of similar, so I'm going to do where name is Joe. So Joe's going to be the one checking the book out. And then in this other set of curly braces, I do $set, so this special function, colon, we'll do checked out has a value of 1 is the serial for Hyperion. Okay. It says right result, number of matched 1, number modified 1. So this query here, whatever query this is, if this returned a lot of things, then it would modify a lot of things. So now I have Joe with a checked out. Yes.
What's the underlying data structure? How is it able to find these keys?
What is the underlying data structure? Right now, the only underlying data structure, I've kind of hidden it by turning off this ID thing. The underlying data structure is something like a hash map on these keys. Yep. So this query that I just did, update where name equals Joe, there was no index supporting that. It had to look at every document, it had to look at every JSON object, find the ones with the name Joe, and then update them. I could add an index on name to make that faster.
So in this case, if you just hard code one checked out, say you want to actually
Yes.
determine what books were available.
Yes. So what if I wanted to, variably find whatever book instead of hard coding it to 1? We'll do kind of the reverse of that, where we will find who has checked out a certain book. But basically, you write a custom function that goes and finds all the things you want, and then you write another custom update thing that uses all that information and goes and updates. Was there another? Okay. So let's do that. Now we have Joe has checked out a book. Now let's say we want to find all the holders of a certain book, or who has checked out a book, or what books are checked out, something like that. Some kind of query that you could easily do with a join in SQL. Let me just show again. This checked out, I completely made up that name, I completely made up that field. The system has no idea what I mean by that. I cannot do a natural join to go and find the name of this book that they have checked out. So this is where it's more open-ended, and we have to kind of do our own interpretation. We have to know what the data means and write our own functions to deal with it. So first we need to find the serial number. So say I want to find all the people who have checked out Hyperion. So I'm going to make a temporary function, and there's var in JavaScript. I'll call it Q for query, kind of like in link, equals db dot items dot find, and I want where title is Hyperion. Okay. And then so that's kind of my query that will give me all of the things where title is Hyperion. So that first line just made that var Q. Now I can say, what is the value of Q? But it's the entire book. I only need the serial number to go find who has checked it out. So I'll go and change what Q is, and I'll do dot to array, and then I only want the first one. This is kind of hard coding, like I know there is going to be one of them in there. And I only want the field called serial. So now Q just has a value of 1, and I've saved that into a variable. Now I can do the other part of the query. So db.patrons.find, where checked out has a value of Q, that variable I just made. And it finds Joe. So kind of more manual, more just kind of like programming. I just kind of did that, made up this query. It wasn't automatically supported by a join with a where and things like that. Yeah.
So this would make 2 different queries to the database.
Yeah.
Right? Call that function, and then returns the value, and then you have to insert it back and then do it again.
Yep.
So do people just write like scripts to get certain values?
Yep, basically you write, it's more like a custom programming language. You write your own queries using a more open-ended general purpose language. And I keep saying it's like JavaScript. It is very similar and even has some JavaScript in it. It's not actually just JavaScript. Yeah. So this var, this var Q that I defined right here, you can just write, some arbitrary code that does some query, and then you can combine that with some other code that does some query to make your database queries. You do have to pay attention to performance. If you have tons of data and you're just doing these weird queries, you don't have indexes in the right place, then same as with an SQL database, it's going to be slow. Yeah.
Another question I had, you showed that at least one place that thought that maybe 80 to 90% of data is unstructured that would use this kind of format. Do you know what that translates to, about what percentage of databases are
So that Merrill Lynch number estimate was for totally unstructured data. This is semi-structured data, meaning I at least have the names of fields. What that estimate was talking about was just completely like unknown arbitrary data that is mostly like human generated, not computer generated. So things like emails, it mostly would come down to AI in order to be able to like truly do anything with all of that data. Or have some person manually go in and figure out how to programmatically extract information into a semi-structured or structured format that a computer can do something with. Is there a question back there? Yep. How is it more efficient? It's not. I would say it's not. It's not necessarily less efficient. It's more about being able to design it in a way that fits your problem more naturally. And so it comes back to that idea of object relational model impedance mismatch, where the relational model is so strict and rigid it sometimes just doesn't work very well for the programming model. JSON is just objects, like objects with any fields and titles. You can easily serialize that into a programming language object. You can do whatever you need to do with it, serialize or deserialize. So there's essentially a more automatic and direct link between the code and the database. Yeah, so if you wanted to use Mongo in a higher level language, it would look kind of like JavaScript. So are there APIs in C#? I don't know. In C++ probably. But basically, you would kind of like import JavaScript queries that interface with Mongo, and then the API would give you a bunch of JSON objects out. Okay. So, kind of recap and like, why would you use non-relational? When would you use relational? It really depends. It's not that one is always better or worse than the other. One problem with, well, it's a problem and also kind of a win. Non-relational databases are easier to scale to clusters, like multi-machines or distributed computing. Part of the reason for that is they don't have all these constraints that always need to be, these consistency constraints. If you have a database that's distributed across multiple machines, and you do like a foreign key update, how do you push that to all the other servers? The reason that's difficult is because of these ACID rules. Non-relational databases kind of never started with ACID in the first place, so they take advantage of that, and it's easier to distribute them across a cluster of machines. Some of them are more strict than others. Some of them do what they call eventual updates, where if you update it on one server, it'll show up maybe within a minute on another server. And in the meantime, you could either maybe mark it as out of date or maybe just return old data or something like that. Depends on what you need. The advantages. Data, especially in the modern era, is not only massive, but unpredictable and changing. Rigid schema definitions make this difficult to deal with. And modern web applications, especially web applications, need to be kind of more agile. Drawbacks. It's a lot easier to mess up. It lets you do anything you want, which is bad unless you're the best programmer in the world. The data, it doesn't have these consistency rules and models, so it's harder to reason about. It's harder to prove anything about it. Usually lacks ACID. They're usually not even using transactions to do these things. And SQL is standard. Everyone knows SQL. I mean, everyone that's in the database world knows SQL. Pick any SQL implementation you want, and it's going to pretty much do what you want. Kind of the most important thing I would say, though, is that it's harder for you and the database system to reason about the queries you're doing. If there are rigid rules, it's easy to reason about. If there aren't, it's hard. So in reality, it's not like a company's going to pick one or the other. I would be willing to bet that Facebook uses some SQL, some document database, and some graph database. Maybe also, probably also some more basic key value store database. They use them where they work best, and they use other things in other places where they work best.
Does MongoDB, does that support joins?
Does MongoDB support joins? No. You would basically have to write your own custom function if you wanted something like a join. Okay. So that's kind of wrapping up our very brief coverage of non-relational. Just wanted to give you the idea. They're out there. When you do your senior project, probably at least one person on your team will say, let's use Firebase. And it's good for you to at least know that Firebase is not a relational database. So kind of switching gears again, in not really databases, but in the same realm of big data and the modern era and massive data, I want to talk about other issues with distributing data across lots of machines. So there's the storage issue, there's also the computational issue. But to introduce this, there's this kind of like infographic from 2007. So this is already really old. And it's showing like the green is analog storage and the tan or whatever is digital storage. It started off like obviously back in the 80s and 70s like pretty much all analog storage. And then computers came along. Well, they came along before that, but they started really exploding and basically taking over analog storage. It probably looks even more skewed now than it did in 2007. Point is, we have a ton of data. We have more data than we know what to do with, and more data than sometimes even we can possibly do anything with. So this term big data is not like an official definition of some particular thing. It basically comes down to this idea that it's easier to generate data than it is to use data. Generating data is super easy, right? There's more footage uploaded to YouTube per second or whatever than could possibly be watched by like every person in the world. I don't know. I totally made that up, but it's like YouTube is generating a ton of data. Phone companies are generating a ton of data. Facebook, everything is just making all this data. Here's an example from Google. I don't remember when this was. I think this was about 10 years ago. So you apply the standard computer technology growth to this. But so 20 billion web pages, and assume they're about 20 kilobytes each. That's 400 terabytes of data. Say you wanted to do something with all of that data, like Google does. Google wants to index every single web page on the internet and be able to search through every single web page on the internet and find things. The average computer can read about 100 megabytes per second from disk. So doing that on one computer would take about a month and a half just to read the data from disk into the processor. That's ignoring all the network traffic and everything else. So another example, AT&T generates 197 petabytes per day. I'm not saying they store all of this, but like all the information transmitted across their network is just massive. AT&T would probably love to do something with that. NSA probably thinks that they can and will do something with all that information. And they would love to be able to store all of that and do something with it. So the solution is you have to parallelize. You can't do this with one computer. Thousands of servers, thousands of disks means you cut down that 1.5 months you divide it by 1,000. Now it's more reasonable. You can do it. You can read the data at least in 1 hour. So problem solved, right? Except that's just reading the data. How do you actually program this? How do you go and find the right data from whatever disk on whatever machine? How do you compute something with that data on your one server, and then combine it with all of the other results that every 999 other server is somehow doing? This is a huge challenge. And you could imagine, well, start writing some C++ program that opens the socket and starts transferring some data, and you could, in theory, write some code that does this. But just as with other computational problems have been solved by tools and languages, this has recently become a big computational problem, and people are making tools and languages to deal with it. Here's another challenge, though, that so it's not just about programming this thing. When you're dealing with thousands of servers, you have multiple failing like every day. So let's say you're running some giant distributed computing thing where you want to answer some question about every single web page on the internet. And it takes a few hours to do that. You're going to have a few failures within that amount of time. How do you deal with those machines? Maybe they were working on something when they failed. How do you know they failed? How do you recover from it? How do you reproduce their results on some other working machine? Lots and lots of problems here. And then finally, this is all going to just burn up tons of energy. So I've said before, there's more money spent in energy than on actual equipment in a data center. Energy to run the equipment and cool the equipment. And the EPA is very aware of this and is actually quite concerned about this and is kind of targeting data centers for how can we cut down on energy usage. Okay, so basic idea behind distributed computing is you have a giant job that you need to break down into smaller jobs for lots of machines to work on. So say you have n jobs, you have s servers. The most basic thing you can do is somehow give each server n over s jobs. So let's look at super basic example. We want to compute prime numbers. And let's say I give server 1, I say you work on prime numbers 1 through n over 2, and server 2, you work on prime numbers n over 2 through n. So let's say that the single machine version of this takes 1 hour. How long does the 2-machine version take? Half hour, 40 minutes? I'd say it probably takes about 59 minutes. Because computing the primality of a number is proportional to the magnitude of the number. I've given server 2 every single number that is bigger than every single number in server 1's work pool. So this comes into the problem of how do you distribute the work. Just naively dividing it may not result in equal amounts of work. So this is called static workload distribution. We need dynamic workload distribution that is smarter. It can keep every machine busy. And the basic idea is you need to break it into smaller tasks, even like more tasks than you have machines for, so that if one of them finishes early, it can pull another task. It kind of just looks like this. If I statically divide it 2 assignments, and one of them happens to be larger, then I'm necessarily going to take as long as the longest job. So you need to make the longest job shorter. But now what that does is I don't know ahead of time what I'm working on. I don't just have my one job and I start working on it. Now you need, and remember there are thousands of servers here. You need to somehow dynamically distribute jobs to tens of thousands of servers and do it all in such a way that nobody gets the same job, nobody works on the same job twice. So you have maybe one machine just dedicated to tracking these jobs and handing them out to the worker machines. Alternatively, so maybe in this model the servers are asking the work servers are asking the job server for a job to do. An alternative model is kind of like the job server tells the worker servers what to do instead of them asking. And then it kind of puts more responsibility and more capability on the job server to decide who does what. This is what's going to allow it to more easily handle things like what if a server crashed. Now the master server is the one that's responsible for knowing that and deciding who to give jobs to. Okay, and then how do we combine the results? So we have 10,000 intermediate results from each of the worker servers. I get all of those results back. I have to combine them in some way. With our simple like prime numbers example, that's trivial. It's adding a bunch of numbers. But what if each of these jobs was take a large document and filter it down into some set of certain keywords? So there might still be a large number of keywords in there. And then you want to count the occurrence of every word. So even that, after it's been reduced, that still is a fair amount of work to do, times 10,000. So that's kind of just giving you a broad overview of like what are the challenges. One of these solutions that I mentioned, people have been making tools and languages to address this. One of them is called MapReduce. Have you heard of this? It was all the rage like in around 2006 to roughly 2014, something like that. Had almost a 10-year run. And then people were like, MapReduce sucks and we're going to do it the better way. But it's not that it sucks. It's like, it kind of put a lot of good ideas out there, and then it's such a new area that people were easily able to improve on. But what it is it's a programming model plus a system to support this like job distribution and result collection problem on a massive cluster. So the basic programming model is, well, this is the basic procedure. Read the data off of thousands of disks. So that by itself is a hard challenge. Where is the data? And then you invoke a map function. So that's the user part. And then the system gathers all of your mapped data and distributes it back out to all the servers for the reduce function. It's kind of two phases. There's like a big filter, give me just the information I'm looking for, and then the reduce is take that information and aggregate it in some way, like a sum or an average or whatever. So these orange parts are the user part, black parts are just automatically handled by the system. So all you do as a user, you write two functions. You write map and you write reduce. And then you kind of make a config file that says, here are all my servers, solve this problem. Okay, so we will get into, before we get into an example, it's kind of a big, we don't quite have enough time left for it today, only a few minutes left, so I will stop there, but we will get into like more concretely, like what is MapReduce, what kind of problems does it solve. But that's it for today.